Okay, so I will be telling you about factoring sparse polynomials. This is joint work with Vishwas, who's my student, and Ilya Volkovich. Good. So let me tell you what the setup is. So we're given as input a multivariate polynomial, and instead of a total degree bound, let's think the polynomial has an individual degree bound. So in each variable, this polynomial has degree bounded by d. So the total degree is at most n times d. And I say the polynomial is a sparse polynomial if it has the sparsity is the number of monomials in it, the number of monomials with non-zero coefficients. So it's sparse if it has only maybe polynomially many monomials, so not too many monomials. So here's an example of a polynomial with sparsity 4. And in general, the sparsity can be exponentially large. So if the individual degree is d, the max monomials is d plus 1 to the n. So in particular, in general, it could be very large, but we'll focus on sparse polynomials. Good. So that's the setup. And this is a very, it's a well-studied and extremely natural complexity measure of a polynomial. How sparse is it? Okay, so this is the notion we'll be looking at. And again, it seems to be a very natural question. If you have a sparse polynomial, how sparse are its factors? Can its factors be much denser, or can you say that sparse polynomials must have sparse factors? So this is the question we want to study. And here's an example of a polynomial and its factor. So this is an example from a long time ago, which was observed and probably observed even earlier than that. If you look at f, the polynomial f being this, so it's a product over all n variables of xi to the d minus 1. Then this is a factor. It's easy to see that this is a factor of that polynomial, right? So because each term out there factorizes as xi minus 1 times this, and so so g is a factor of f.
It's most impressive when n equals 1, right?
It's most impressive when n equals 1. Good. So when n equals 1, f has just 2 monomials, and g has n or n plus n monomials, or d monomials. So that's so good. But yes?
Do you consider the field, the ground field here? So because of, for instance, for one variable it is very different.
Yes. So the
factors over q.
So good. The field is it's interesting to question. So whatever I will talk about will be field independent, but definitely the field does play a role. It could be that over certain fields, sparse polynomials may have sparse factors, but over other fields they may not. So the field is a really important player in the background and for what might be true, though whatever the results I will talk about won't use the field, and which is somehow unfortunate. I think if it does use the field, maybe you can get much stronger results.
So your results will hold over the integers?
Yes. Oh, integers, I mean, yeah, sure. We'll see what I, yeah.
But then this isn't an irreducible polynomial.
So good. So I'll say something about that as well. So good. So if n was just 1, then f has 2 monomials, g has many more monomials. So of course the sparsity can blow up a lot. But if for us a sparse polynomial is one which has polynomially many monomials, then if you set n equal to 1, you're not noticing this big blow up unless the degree is very large, maybe super polynomial or exponential. So let's always think of the degree to be bounded at least polynomially. And in this case for a univariate polynomial, you don't have the super polynomial blow up with one variable. So to observe a super polynomial blow up, you just increase the number of variables. And here you'll see that, so this, if you have n variables, then the sparsity of f is 2 to the n, and the sparsity of g is d to the n. So a super polynomial blow up in the sparsity. So the sparsity of g is f to the log d. So if you think of d to be polynomially large, then there's this quasi polynomial blow up in the sparsity.
And that's the best example now.
That's basically the best example known, yes. So do I say that? So this is essentially the best example we know in terms of the blow up, and it was conjectured that maybe this is the best we can do. Maybe for any sparse polynomial, each factor can be have sparsity or density or whatever. The number of monomials can be only quasi polynomially larger. We don't know the answer to this question. I think this is really interesting.
And with irreducibility, possibly there's an even in the polynomial form, or you don't know?
Good. So the swastics question is, so notice that G is not an irreducible factor of f. G is a product of lots and lots of polynomials. I don't know any example of G dividing f where G is irreducible and has this big blow up.
I mean, if you take the field to be Q, then it's irreducible.
It's still a product of n things.
G is still a product of n things.
Why the roots of unity actually?
No, it's written as a
product of
product.
everything.
It's
Oh,
written
I
as
see,
a
I see.
product.
Right. So it could be that the irreducible factors are much sparser. Maybe there's no blow up. I don't know any examples. So, but for just general factors, you can't hope for a polynomial bound. Here is another example. So this was the example. This is in some sense the best known, but here's a bit of a weird example. So P is prime, and we're working over Fp. And look at f to be summation xi to the p. That's the same as summation xi whole to the p. So for any d between 0 and p, summation xi to the d is a factor. Okay, so the sparsity of f is really small. It just has n monomials. But G is very dense, right? Because say pick D to be p minus 1, and this big simplification which happens in the case of f doesn't happen anymore here. The sparsity of f is n, and the sparsity of G is something like n to the d. D can be almost as large as p. Basically, n to the p. So there's this, instead of a log d blow up, you got to blow up by a factor of d. So if d was large, if d was like polynomially large, this is an exponential blow up in the sparsity. And I say this is a weird example because the degree of f had to be something very carefully chosen as a function of the characteristic of the underlying field. So this weird example, I only know this one weird example, and it's only when basically the degree is as large as the characteristic, and you're playing funny games with the degree and the characteristic.
Can't you do it for any powers of P as well?
You probably can, yeah.
Doesn't do it. So then you
It can be
make
power
it
of a
as
prime.
large as you want, right?
Pardon?
So then it's not really a constraint on D, right? You can give an example for whatever D you want. basically.
Right. But so you can't. This example first of all doesn't hold over characteristic 0, and it wouldn't hold. Right. Without if your degree, the characteristic of the field was much larger than the degree, then it wouldn't hold. But if your degree is mixing with the characteristic of the field in some funny way, then you can create examples.
Sort of cheating.
Sort of.
But you have to watch for it when you're moving up or down.
Right. But it's sort of cheating, sort of not cheating, whatever. But this example, we only one interesting fact is for characteristic 0, the previous example was the only example we know. And if for fields of small characteristic, you can do other weird stuff. And so basically in this case, there's no good sparsity bound because the blow up can be so large. It's exponential in D.
Unless again you look for irreducible factors.
Good. Unless again you look for irreducible factors. So even in this example, this factor G is highly not irreducible. Right? G was a product of lots of things. All the irreducible factors of f were still very sparse. So it could be that always, if we only care about irreducible factors, it could be that they are always sparse. But I don't really know how to work with irreducible factors. So I won't be able to see anything meaningful, and I don't think anything meaningful is known.
But a reasonable conjecture is
It's a reasonable conjecture that for any polynomial, any field, any degree, all the irreducible factors are very sparse. Yeah. I don't know any counterexample. But and for general factors, the best two examples I know were characteristic 0, the previous one with a log d in the exponent blow up in sparsity. And if you want to do weird things with the field, then basically you can have this big dense factor. Good. So in general, yeah. So if the individual degrees, if this little d was large as n or something, then the factors of f can have exponentially many more monomials than f. And in characteristic 0, a large characteristic, maybe this quasi poly blow up is tight. And so both these settings are very interesting. I, in general, won't be able to say anything about it. The focus of this work will be, let's think of this individual degree d to be small. Okay, so imagine this individual degree was 10. You can even then ask the question that you have a polynomial, the total degree might be large, it's 10 times n, but each individual degree you're bounding by 10 or log n or whatever, it's small. And then are those examples the best examples?
Is it clear that there is any bound in terms of the number of monomials?
No, so a priori you could have, so the sparsity could be d plus 1 to the n, right? So right at the beginning, if the individual degree is d, then the number of monomials can be as large as d to the n or d plus 1 to the n. And there's no, I mean, at least before our work, there was no reason, we didn't have a better sparsity bound than that. It could be that you have a polynomial with n monomials, and the factors have d plus 1 to the n monomials.
No, I just meant if the number of monomials is 5.
Uh-huh.
Is it clear that there is a bound in terms of 5?
No, because x minus 1 to the d, the first example, we go from 2 to d.
2 to d. So d is anyways, but so d, you can always get d from 2 to d.
Right,
Yes.
so okay, yeah.
But
So it is independently set the degrees.
yeah, it used to depend on, yeah. Good. So even if this individual degree d was 5 or whatever, something very very small, a priori there's no it's not clear why there should be a better sparsity bound. I mean, there was no sparsity bound. It could be that you have very sparse polynomial whose factors are still exponentially dense. But what we do, okay, so let me say what prior work was known. So for very small values of d, for d equal to 1 and d equal to 2, there was, prior to our work, there were these works. So d equal to 1 is multilinear polynomials, and d equal to 2 is multi-quadratic polynomials. Each variable has individual degree 2. In both these settings, we know, we know good sparsity bounds, that the factors are have at most as many monomials as the polynomials themselves. And they are easy proofs by induction to show this, like 2-3 line proofs in both cases. There was a paper by Oliveira, that's very nice work, which looked at factors of polynomials computed by small depth circuits. So in particular, he showed more than this, but one thing he showed was that if you start with a sparse polynomial with small individual degree, d being small, then its factors have small depth 7 circuits. What we are trying to show is start with a sparse polynomial. A sparse polynomial is a polynomial with a small depth 2 circuit, because a sparse polynomial is a sum of products, and if the number of monomials is not too many, that means there's a small depth 2 circuit that computes it. So if you want to show that factors of sparse polynomials is sparse, that would mean small depth 2, the factors of small depth 2 circuits have small depth 2 circuits. So what Raphael showed was that they have small depth 7 circuits. In particular, for any depth, he showed that factors of small depth circuits have smallish depth, smallish lowish depth circuits.
Are you going to give the background of Kaltoffin's result just in front?
Yes. Yeah.
No, yeah.
I will talk about Kaltoffin's result also. Yes. But just for the sparse polynomials, yes. So I'll talk about, good. And for sparse polynomials, factors of sparse polynomials are sparse. Zev and Raphael had a very beautiful approach to understand this question, and our results will be inspired by this approach. So there was an approach which eventually did not work out, but many of the ideas which went into that approach inspired us, and we build upon it and get our results, which I haven't talked about yet. So this is what we show, that let f be an arbitrary field, and f is a polynomial which is S sparse, so S monomials, and the individual degrees at most d. Then every factor has sparsity at most s to the d square log n. So if the d square was the d and there was no log n, then you can't do better than that. That second example, that second weird example I showed. Is that a question? No. Yeah. So if that second example shows that so s to the d is a lower bound for general fields, we are able to show that get a bound of s to the d square log n. So since you're not looking at the field, this is sort of tight, like the dependence on d is basically correct. The s to the d is the best lower bound we know. And so that's our result. So this is getting back to Avi's comment about putting it into context with Kaltofen's work. So in general, you can ask, if you have a polynomial of low complexity, do its factors have low complexity? And what can you mean by low complexity? So there was beautiful works. Kaltofen showed that if your measure of low complexity was computable by small arithmetic circuit, then this is true. Any polynomial that is computed by a small arithmetic circuit, any polynomial of maybe polynomial degree computed by a small arithmetic circuit, its factors are also computed by small arithmetic circuits. And this is really, really beautiful work, highly non-trivial.
And moreover, it's a corollary of the fact that there is an algorithm, a fixed algorithm producing the factors.
Right. Not only did he prove this result, he also gave an efficient algorithm, randomized polynomial time algorithm to compute the factors of a circuit represented by a small, to compute the factors of a polynomial represented by a small arithmetic circuit. There was this recent work by Mrinal and somebody else, I don't know which, I think Noam Solomon, yeah, giving I think a simpler, I haven't looked at it, but I think they claim a simpler proof than Kaltofen's proof and self-contained, but not giving an algorithm. So there's a direct simpler proof of just the closure in VP, that the factors of polynomials in VP are also in VP. There's this, I think now there's a simpler proof. Oliveira, so the same result I talked about, he showed that your constant depth circuits of small individual degree, they're also closed under taking factors. The factors are also constant depth circuits of small individual degree. And very recently, there were two different papers showing these closure results for polynomials in VNP. So you start with the polynomial in VNP. Those of you who don't know about it, I won't talk more about it, so forget it. But if you know what VNP is, if your polynomial is in VNP, the factors are also in VNP. And these results also talked about ABPs and formulas. But again, I don't want to get too much into it. But recently there's been a lot of work on these closure results. And what we show is closure results sort of for depth 2 circuits of bounded individual degree. You start with the depth 2 circuit, small individual degree, then its factors are again depth 2 circuits of small individual degree, but with a quasi-polynomial blow up.
So we still don't know depth 3 circuits?
We don't know depth 3 circuits, yeah. It's a good question. Depth 3 circuits would have your depth 8 circuits by Raphael's work, but yeah, depth 3 we don't know.
That would have some implications more like PAT or hardness randomness. Combined in polyatomic.
Yeah.
You have lower bounds for depth 3, you get PAT for depth 3.
But even with PIT, for the factoring for depth 3 is still, even if you know lower bounds and we can talk, yeah.
At some point you might
Right.
get applications for
Right.
optimization.
Right, right. So I'm not aware of anything immediately, but yes. Okay, so we have the sparsity bound. We're also able to get an algorithm. So Kaltofen's algorithm, I said he gave an algorithm for factoring. So small arithmetic circuits have factors which are small arithmetic circuits, and there's an efficient algorithm. That algorithm is randomized. We give a deterministic algorithm for the same class of polynomials. So we show that if you have a sparse polynomial of low individual degree, we know its factors are again sparse, so they can be efficiently represented. But we show that we can deterministically even compute these factors in time. If D is small, again this is the same quasi polynomial blow up times polynomial in the field size, which is is somehow seems necessary. If our sparsity bound, we get rid of the log n there, we would get rid of this log n here also. So once we have the sparsity bound, we investigate Kaltofen's algorithms from the past and see how to make, if we can go and use the sparsity to de-randomize those algorithms, and we're able to do that.
You really need the poly f. I mean, if the field is f2 to the n, you really need.
Good. So no. So this we don't.
Yeah.
This is the same for univariate factoring, whatever f poly in the characteristic of the field. Maybe
you
this
just
is
need to be able to
right.
do arithmetic in the field.
Right.
That's
Right.
better than poly f, yeah.
Better than poly. Poly in the I believe it's poly in the characteristic of the field.
You
Whatever.
just need to do arithmetic in the field. That's all.
That's right.
Yeah.
That's right. That's right.
Probably finding the roots of univariate polynomials. That's not just arithmetic, that's algebra.
But it's poly characteristic of the field.
That's poly
Characteristic of the
No,
field.
you're right, yeah,
Right.
and you
Right.
need to find it.
Yeah. Good. So we'll show this. So the plan of the talk, I'll first prove the sparsity bound, and then I'll tell you a little bit about factoring algorithms, and then we'll see the proof of the deterministic factoring algorithm. And along the way, as I tell you about the deterministic factoring algorithm, I'll tell you a little bit about Kaltofen, Traeger, and the factoring algorithms of the past, how they worked, and how we de-randomize it in our setting for sparse polynomials. Okay, so let's jump into the proof of the sparsity bound. So f, g, and h are three polynomials. F is g times h. We want to show that if f is again s sparse, each variable has degree d, then the factors are at most s prime sparse, where s prime is that bound. Right? That's what we want to show. We will show this slightly more general result. That suppose g is any polynomial of sparsity s, and f is g times h. So g has s monomials. Then the number of monomials in f can't be too few. We started with saying if f has few monomials, g can't be super dense. We're just saying this, flipping it around, saying g has s monomials, f can't be super sparse. So I want to say the number of monomials in f, if f is g times h, then the number of monomials in f is at most s times 1 over d square log n. And this is slightly more general because originally we had a sparsity, this individual degree bound on f. An individual degree bound on f implies an individual degree bound on g and h. In this slightly more general version, I'm only imposing a degree bound on g. H can have arbitrary degree, and hence f can have arbitrary degree. So we won't care about the degrees of f and h as long as g has small individual degree. We want to show that then as long as g is a small individual degree and sparse, there's nothing that we can multiply g with which will have this overwhelming cancellation of monomials to give a very sparse polynomial. So this is what we're going to show. Okay, so that's the plan, and the proof will be via convex geometry. So this is what the setup is. A polynomial. So suppose so just to set up some notation, if your polynomial is presented to you as a list of monomials, we'll say the support of the polynomial is those set of monomials which appear with non-zero coefficient, let's look at their exponent vectors. So for instance, if I1, I2 up to In was some monomial in F with a non-zero coefficient, I look at its exponent vector, this n tuple, and I toss it in to my support set. So I collect the supports of all the monomials and call that the support of F. I don't care, I throw away the information in the coefficients of F. I just look at which monomials appear and the Good. And now given the support of F, so given a polynomial F, I can define the Newton polytope of F to be, let's look at these support vectors and plot them as points in R to the n. Okay, a whole bunch of vectors in R to the n, I take their convex hull, that's the Newton polytope. So my original polynomial could have been over any field. I don't care, I throw away the field information, I throw away the coefficient information, I just look at the supports of the monomials, I view them as points in R to the n, and I look at the convex hull, I call that the Newton polytope of the polynomial. Questions?
You call it and everybody calls it.
This is the Newton polytope of the polynomial. Good.
For the rest of the proof, you're only going to talk about
Yes, interestingly enough, we will never look at the coefficients again, we will never look at the underlying field again. This Newton polytope will basically capture the complexity of everything.
And F will be G.
F will be G, but this is just fair notation, yeah. But we basically will ignore now. This is why we're not really using the underlying field because we're not even looking at the coefficients. We'll focus on Newton polytopes.
This is going to be something about the extremal points of the Newton polytope.
It's just going to be about the extremal points of the Newton polytope. So here's an example. So if F is this polynomial, then this is the Newton polytope because there are four monomials. So the four support vectors we picked up were 0, 0, 0, 2, 2, 0 and 2, 2. And so this is the Newton polytope of that polynomial. Okay, good. So let me tell you some properties of the Newton polytope. So the most important and interesting fact about Newton polytopes we will use is the following, that if F is G times H, then the Newton polytope of F is the Minkowski sum of the Newton polytope of G and the Newton polytope of H. It's a beautiful fact, not very difficult to prove. So if there's interest, maybe at the end of the talk, if anybody wants to see the proof, maybe I can try to do it. This is not it just needs some simple polytope convex geometry facts. Nothing very serious, nothing very deep. It's probably an exercise. If you're comfortable working with polytopes, it should be an easy-ish exercise to prove this. Good. Everyone's happy with that? Here's another fact, probably folklore, that okay, so for a polytope P, I'll let V of P be the vertices of the polytope or the corner points of the polytope. Then if you have two polytopes A and B and you create the Minkowski sum, everyone's happy with Minkowski sum? It's just the pairwise for every point in A and every point in B, you look at the vector obtained by summing these two, the sum of these two vectors, and you look at all the sums obtained, and that's the Minkowski sum. Good. So look at the number of vertices in A plus B. This is at least the number of vertices in A and at least the number of vertices in B. So the number of corner points can only go up, it can't go down. Okay, this is again it's a half a page or less proof. It's not too difficult to show. Again, if there's time and interest at the end, I can prove it. It's a fun exercise in convex geometry. Okay.
It's probably worth mentioning that it's Ostrowski result and then later results that the connection to convex geometry is old in algebraic geometry. The use of convexity in algebra is old, and they use when you look not at factors of polynomials, but you look at solutions to systems of polynomial equations. Then using this convexity, you get improvements to Bezout's theorem in many cases that are very important. That's the Bernstein result.
Good. So I don't even know about all these. So we should have come and ask Avi about it later. But these are old results, and this connection to convex geometry has been used before, and I think it's a really beautiful connection. So the three facts about polytopes we will use are that fact, this fact, and this easy fact, which is the number of monomials of a polynomial is at least the number of corner points of its Newton polytope. Right? Because it's how do you get your Newton polytope? You took looked at the coefficient vectors of all the monomials and took their convex hull. So the number of corner points is clearly less than the total number of monomials, or the total number of points in the support of the polynomial. This is just an easy trivial bound. But if you take these three bounds and you put it together, you observe the following. So so the total number of monomials of f is more than the number of corner points of its Newton polytope. The number of corner points of the Newton polytope. So Pf, the Newton polytope of f, but if f is g times h, then the Newton polytope of f
should be h.
That's h. Sorry. The Newton yes, those two f's should be h's. Yeah, good catch. Okay. If f is g times h, then Pf is pg plus ph. So the number of the number of corner points of Pf is the same as the number of corner points of pg plus ph. But the number of corner points of the sum of two polytopes is at least the number of corner points of g, and it's at least the number of corner points of h. So that's at least it's the max of the number of corner points of pg and the number of corner points of ph. So good. So let's remember that. And what we want to show is that if g is any polynomial of sparse and small individual degree, then you can't multiply it by h and get this overwhelming cancellation of monomials. That's what we wanted to show. So by that line, the first line, what it suffices to show is that if g is any polynomial s sparse small individual degree, it just suffices to show that the number of corner points of Pg, the Newton polytope of g, is small. Because is large. Because if g has many corner points, if the Newton polytope of g has many corner points, it will imply that the Newton polytope of f has many corner points, which will imply that f must have many monomials. So it suffices. So if whatever our entire sparsity bound has reduced via this convex geometry to showing this statement, that if g is a polynomial of individual degree d and g has s monomials, then we want to show that the number of corner points of the Newton polytope of g is large. Okay, so that's what we'll show. Hence we can strip away the underlying field, coefficients, everything, but just studying the Newton polytope. And I want to say that this connection to showing the sparsity bound via studying Newton polytopes was made by Zev and Raphael, and this approach of ours was, of course, heavily inspired by their work.
So you will use integrality, I guess, of the
yes,
the point, the fact that
yes,
coefficients,
yes,
I mean
yes,
that
yes,
coefficient vectors are integers.
yes. Coefficient vectors are coefficient vectors are integers. We will use that. Yes, of course.
But this seems very wasteful. Is there some reason we should expect it? I mean, does it not become so wasteful when you think of it asymptotically, or?
It is. So our bound is there's not that much. So that d square log n can become a d, right? So it is this. Yes, this does seem very wasteful. We still managed to get via this big wasteful procedure a pretty good bound. But hopefully one can do this better, and if you can account for this waste and you can get a better bound, that would be great.
But just using this data, you might get s to the 1 over d there.
So, well, okay. So let me say that now itself. So wait. So this is what we want to show, right? So I'll come back to what Zev mentioned. So we want to show that the Newton polytope. This is what we want to show. This is what we will show. That if g is any such polynomial, then its Newton the corner points is large. We will show this, and we will derive our sparsity bound from that. Is this bound tight for the thing? I guess Dev's question is this bound tight? As a convex geometry question, is this bound tight? I know that the log n needs to be there, and the d also needs to be there because of the sparsity bound. The d needs to be there. We have an example showing that the log n needs to be there. This d square times log n might be a d plus log n. I don't know, but the d needs to be and the log n needs to be there, so it's basically tight. You can't hope to improve it much. Yeah. So good. This is what we want to show, but for a general polytope, you can clearly not bound the number of corner points in terms of the interior points, right? It's meaning, I mean, this polytope might have, there are 4 corner points, it has some number of interior points. This polytope has again 4 corner points, but many more interior points. So in general, you can't bound corner points as a function of the interior points, but for these polytopes, what we haven't used is the bound in the individual degree. So the individual degree bound is what's going to be crucial. So how do we use the individual degree bound? So note that since the individual degree of each variable is at most d, that means that all these interior points, these coefficient vector, not the coefficient, these exponent vectors of all the monomials, these are, each exponent vector is an element of 0, 1 to the d to the n. So if you looked at the support of the polynomial, the support was a subset of this. And so now we want to show that, so our problem is equivalent to showing the following. Let E be an arbitrary subset of size s, arbitrary subset of 0, 1 to the d to the n of size s. Then, if you look at the convex hull of E, it should have many corner points. Let's forget about polynomial now, and individual degree, etc. Just now, this is completely, you have a set of points, you have a subset of 0, 1 up to d to the n of size s. Then the convex hull needs to have many corner points. That's what we want to show. So I'm just again rephrasing it. If V of E denotes the number of vertices, just notation. If V of E is the number of vertices of the convex hull of E, we want to show that the number of interior points, or the total number of points, is at most the corner points to the d square log n. We are not just saying the same thing. Okay, so good. So this is what our problem is boiled down to showing. Good. So let's get into the proof. It's not a difficult proof. Questions about the statement? Everyone's happy?
There's no constant in the exponent.
There is. Actually, there might be a 3 or 4 or 5 or something is sitting there. Yeah. So it might be 5d square log n. Might be. And the not optimized, it may be smaller than that, but I think 5 is an upper bound on that. But thanks. Okay. Okay. So Carathéodory's theorem is a classical result in convex geometry, which says that if you have if one point is the convex combination of a large number of points and you're sitting in n-dimensional space, then that point is in fact a convex combination of at most n plus 1 of those points. So every point can be written as a convex. So every element of E in particular is a convex combination of at most n plus 1 elements of the vertex set or the corner points. Okay, so this is very basic, again, it's a classical result, not very hard to prove.
So it's like linear dependence but with positive coefficients.
Yes. Yes.
A convex combination is like, it's the sum of the coefficients which sum to 1. Yeah.
It's the duality theorem of linear programming, or the Farkas lemma, or whatever.
Every interior point is clearly a convex. You're taking the convex hull. So every interior point is a convex combination of some of the corner points. But you can always write it as a convex combination of at most n plus 1 of the corner points.
Here integrality doesn't play any role.
No, there's no
Well,
integrality.
yeah.
So that's classical Carathéodory's theorem. Here's a wishful thought. But we don't have an arbitrary subset E, we have a special subset E. In particular, this integrality stuff, plus E is a subset of 0, 1 to the D to the N. So E is a special set. So maybe we can strengthen Carathéodory's theorem. Maybe every point is not a convex combination of n plus 1 points, n plus 1 of the corner points. Maybe every interior point is a convex combination of much fewer corner points. Maybe. That was one hope.
But this will not be enough.
It will not be enough.
Because it can be very different combinations of the same set.
Good. Maybe even more is true. Maybe these convex combinations are actually uniform convex combinations. And I say a convex combination is uniform if it's all the coefficients are the same. This is hope. I mean, and for some time we believed this hope. We weren't able to come up with counterexamples. We said, oh, maybe whatever small examples we had, we have E such a special set. Maybe every interior point is actually a uniform convex combination of much fewer points. If this is true, then we're done.
There are statements about near uniform combinations of.
Yeah. So you should have been working with us on this, and then we wouldn't have been stuck for so long. Yeah. So this is a visual thought, and if this was true, then we would have been done. And the reason we would have been done is the following. If this was true, that means every interior point, every point of E is determined by k of the corner points, right? Because there's some k points whose uniform convex combination gives you this point. So every interior point is determined by these k vertices, and every k vertices on the corner can determine at most one interior point, because these are uniform convex combinations. So the number of interior points can be at most the number of corner points to the k, because there is this injection from here to here. Every interior point you could have associated with it some k tuple of corner points, which determines it. So this would have been enough. Good. So this was our visual thought. This is not true. But what is true was exactly what Avi said. We don't, for every interior point, we don't exactly compute it as a uniform combination of corner points. We show that every interior point can be approximated by uniform convex combination of corner points. Okay, so every point of E we will show is epsilon approximated. Epsilon, we'll think of it being the L infinity norm, but whatever norm, any reasonable norm would have worked. Every point is epsilon approximated by this uniform convex combination of few corner points, d square log n.
And probably already here you lose the factor of d. Like
I don't know if
you
it's.
You need epsilon to be small enough to distinguish different
We need epsilon.
integer points, right?
Yes. Yes. Yes.
If you want to distinguish integer points, the epsilon should be like 1 over n or 1 over square root n.
So right now, I mean, epsilon can be 1/3, right? I mean, every integer point, any two integer points in L infinity norm, it will be in the L infinity norm. We'll be working in the L infinity norm. So in the L infinity norm, every 2 points, and it is in one coordinate your distance 1, so epsilon equal to 1/3 would have worked for us. But still, there's some d we do lose.
If you take just the one-dimensional case, then there are always two corner points.
Yeah.
I don't see how you can approximate every interior point.
Every interior points are integer lattice points, right? 0, 1 to the d. If you're the corner points, the corner.
N is one variable.
Yes.
In this case,
But d is what? D.
doesn't matter.
It matters.
Oh, I see.
Exactly, but the corner points have to be elements of 0, 1, 2, 3 up to d to the n, right? So your corner points can't be far away corner points. In your the constraint on d is squishing all these things into a
So
small
what is the
cube.
constraint on d with respect to n?
Think of d to be 5.
Think of d to be 5.
Yes.
You will have to
D is a
repeat-
parameter, but even it's interesting when d is 5.
You will have to repeat points when you take
Yes.
uniform combination.
Yes.
Ah, okay.
Yes.
So you can take 5 times this corner plus 3 times that corner. Take that out.
Right. Oh, that was the confusion.
I see, okay. Yeah, okay, I see.
Oh, you mean how would you approximate everything? Oh, I understand what you mean. Sorry, good. So yes. So when we show this, these k points of VE may not be distinct points. It will be with a multi-set. You can use. I'll take k corner
And
points.
That's why we e to the k rather than some choose.
Exactly. Yes. Good. So we show that each interior point is approximated by k vertices. So and this will give the same bound once you do this approximation, because every interior point is approximated by k vertices. Every subset of k vertices can uniformly approximate at most one point because of some triangle inequality. So all we need to show is this fact, that every point of E is approximated by a convex combination of not too many points. And if we can show this, we are done. And this, so it turns out there's a paper by Barman. I think it was algorithmic game theory paper.
Earlier results, but
I believe they must be earlier. So they must be. The proof is very easy. So I'm going to give the proof. It's one slide proof. It's in not once you know what you want to show, the proof is not very difficult. We found in this paper. It wasn't in this language. I've reworded it to suit our application, but basically this was something that has appeared before. That let V be a subset where it wasn't important that it's 0, 1. Just the L infinity norm of every vector is at most D. Then for every interior point of the polytope, you can epsilon approximate it in the L infinity norm with a uniform convex combination of the vectors, and the size of this convex combination is d square log n with some dependence on epsilon. Maybe d square over epsilon log n or d square over epsilon square log n. Okay, I'll prove this. This is
Scale invariant. How can B?
It's not scale invariant. It's L infinity norm.
Yeah, but that's in the assumption scale invariant. The conclusion.
But the number of the size of the convex combination is depending on
The
d.
ratio of epsilon and D matters. Okay, good.
This will be d square over epsilon square log n, I believe.
Yeah.
Yeah. So let me prove this again. It's an easy. And let's call it the approximate Carat theory theorem. There's approximate versions of the these approximate Carat theory theorems. This was the L infinity approximation. If you Google for approximate Carat theory theorem in the LP norm, there's lots of works, and they're much more complicated and difficult. But we didn't need all of that. In the L infinity norm, the proof is just easy. So this is approximating in the L infinity norm, much simpler than LP norms, and it's just a simple Chernoff union bound argument. So. Good. So let's prove this. So let's take any interior point, and I want to approximate it by a uniform convex combination of few vectors. So let's take mu be any interior point. So mu by the Carat theory theorem or whatever, mu is a convex combination of some of the corner points, right? So mu can be written as summation ai vi, where vi are the corner points. The ai's are non-negative and they sum to 1. Right? This we know. So now we can think of these AIs to be a probability distribution. This non-negative is sum to 1, and the probability of sampling VI is AI. So just sample the VIs from this probability distribution. Sample 100 d square log n samples. 100 should be 1 over epsilon square maybe. Yeah, if you want to if epsilon was 1/3 and you just want to do the 1/3 approximation, which will work for us, something like 100 d square log n samples would work. You take a whole bunch of samples from this distribution, so you get a whole bunch of corner points. Take their uniform convex combination, and I want to say that approximates my chosen interior point well. And this is I want to show it approximates in the L infinity norm well. So every coordinate it should approximate well, and that's a Chernoff union bound. Simple Chernoff union bound. I mean the very basic Chernoff. The log n comes from the union bound. We want to approximate it on n coordinates. That's where the log n comes from. And the d square comes from. I mean you want to approximate it. These are the vector in each coordinate. The vector has L infinity norm d. So that's where the d square comes from. If you scale everything to be L infinity norm 1, then you would have to 1 over d approximate it, and that's where the d square comes from. You needed a good enough approximation on each coordinate.
1 over epsilon square.
D over epsilon whole square. Yeah. There would have been it should be d over epsilon whole square, and the log n is from the union bound. You need the approximation to be good enough that it holds. or with high enough probability that you can union bound over all n coordinates.
And if you just did the calculation in L2 norm, what will be the bound?
Will you get better or worse?
So L2 norm, so one is if you have a good enough approximation on every coordinate, then you can do union bound to do the L2. That's
Or
it?
you can win something because in L2 norm you can have a small number of points that are
Bad, yeah.
close,
Yeah,
but
yeah,
that's fine.
yeah,
I mean, you
yeah,
lose the
yeah.
not-
So I tried that. I don't remember off the top of my head, but when we got this, it seemed so wasteful. I mean, already, I mean, is this d square log n tight was a question then I thought about a lot. Like, can you, this slack, exactly this L2, maybe you don't have to approximate in all coordinates. Maybe in 99% of the coordinates you approximate, and maybe that's enough. And maybe, so getting rid of this log n I thought is the most, so the d is necessary. Is the log n necessary? And we didn't know it was necessary, and we tried a lot and weren't able to do it. Ram Prasad Saptarishi came up with an example which shows that the log n is necessary. In this convex geometry question, this log n is necessary was something he showed, and it's a very nice example. Maybe it's worth, I'll give you the example. Where he gives an explicit set of n corner points with n to the log n interior points. So I'll tell you that example. And so the d is necessary, this log n is necessary. So how much can you? But I think it's still interesting to understand what the right dependence is. But you can't help avoid the d, and you can't help avoid the log n.
So the counterexample is d equals 1?
Pardon?
The example you said with the log n.
Has d equals 2, 3, 0, 1, 2. D equal to 2.
So you didn't really need Carathéodory's theorem.
I didn't really need.
N plus 1.
No, but this n log n.
But the log n is the n coordinates, not the n.
You're right. Yes. Yeah, the Carathéodory wasn't needed. It's just approximate, so it's nice to think about Carathéodory, but it wasn't important that this was n. Sorry, this n wasn't. It could have been anything,
Yeah.
but right. Okay, let me actually give you this. The example, maybe I won't prove all the details, but let me tell you what Ram Prasad's example is. So let's look at, let n be 2 to the m, and we look at the n by n Hadamard matrix. So you think of every column and every row being indexed by a vector in f2 to the m, and A, B, so you have for A and B in f2 to the m, the AB entry of this matrix is -1 to the inner product of A with B. So it's the n by n, it's the +1 -1 Hadamard, n by n Hadamard matrix. Good. So let's call it H. So let V be the set of columns of this Hadamard matrix. This is a subset of -1 +1 to the n, right? These will be my vertices. We think of this to be the vertices of the polytope.
You don't blow them up by details, or you just these one.
These two. So this is, I'll shift it. Eventually I will shift it. My polytope will be a subset of -1, 0, 1 to the n. I'll show that the interior, this is n corner points. If you show this as n to the log n interior points, then I can just now take this polytope and shift it to be a subset of 0, 1, 2 to the n, and I'll have n to the log n interior points. So these will be the vertices of the polytope. It does prove, but let's keep that on any up. Okay, good. So n vertices, and now we will see why there are lots of interior points. So the interior points, so of this polytope are going to be, we're going to take a bunch of, so each interior point has to be a convex combination of some of the corner points. We'll derive these interior points as uniform convex combinations of the corner points. And the way Ramprasad does it is, let S subset of F2 to the M be a subspace. Okay, so let's take any subspace of F to the M. Let's look at all the vertices corresponding to elements of that subspace. And let's take their uniform convex combination. That turns out to be an element of 0, 1 to the N. So
but S is in F2, and now you want to look at real vectors. What are
that's it. S is going to index a whole bunch of vectors of V, right? Every row and column is indexed by an element of F2 to the M. So S indexes some subset of columns of H, and the claim is, let's look at those columns and take their uniform convex combination. So maybe if U sub S is the characteristic vector of S, the subspace, let's look at this Hadamard matrix times U sub S. So I'm just taking, and let's do 1 over size of S times this. So I look at all the columns indexed by the subspace, and I take their sum and I divide it by the size of the subspace. So I take the uniform convex combination, and I get a vector, a real vector, right? Because I took a bunch of vectors in the reals, I sum them, I took the uniform convex combination, and the claim is this belongs to 0, 1 to the N. So this is an interior point of the polytope, right? I took a whole bunch of vertices and I took a convex combination. So this is an interior point. It turns out to be an integer point. So it fits it is in our lattice. So that's the claim. So this is what he observes. For every subspace, the convex combination gives you a vector, and it give you distinct vectors.
Does this give a polynomial with a sparse?
It doesn't. So that's a very good question. So this shows that the geometry question, the log n is necessary. For the geometry problem, maybe that this log n is necessary because this gives you a polytope. This is the claim. This and distinct S's give you distinct points, and the total number of subspaces is n to the log n. Okay, so this is now, once I tell you what this is an exercise to show.
You take a polynomial with these coefficients.
So I don't know.
You pick a field.
It's a good question. I don't know.
I
I don't know. So that's a great question. Is that log n necessary in the sparsity bound? So can you come up with examples of polynomials where the sparsity blow up needs a log n? I don't know this. So this Ramprasad's example gives you a polytope with few vertices, many interior points. Can you translate that into a polynomial whose factors are dense? I don't know. I've tried a bit, not too hard, but nothing seems hard to do that. But that's a great question. So the log n is necessary in the geometry question. The log n I don't know is necessary in the sparsity bound. The d square log n can just be a d in this, as far as I know. Yeah. Good. So that completes the proof of the sparsity bound. So that's all I want to say about the sparsity bound. And yes, is it tight? Maybe that's the next slide. Yeah, is the sparsity bound tight? Because that's still a very interesting question, and we don't know. We get the d square log n. As far as we know, it can maybe only a d because of that crazy example on my second slide. And again, if it's irreducible factors, maybe you can do something much better. If the characteristic is 0, maybe you can do much better. So there's lots of, I think these are all very, very nice questions, and as far as I know, they're completely not understood at all. Okay, so second half of the talk, I'll talk about the factoring algorithm. How do you go from this sparsity bound to come up with a deterministic factoring algorithm for the same class of polynomials? Good time for a break, probably, right? So let's take a break and I'll tell you. And you need to either decide whether the polynomial is irreducible or output a factorization. And this is again a fundamental important problem with lots of applications. So let me tell you a little bit about the history. So in again a beautiful sequence of works, Kaltofen showed how gave an algorithm, a randomized white box factorization algorithm for polynomials. So he gave a randomized algorithm where given as input an arithmetic circuit, a small arithmetic circuit, you can output. He gave an algorithm, a randomized algorithm for outputting circuits, small circuits for the factors of the polynomial.
So what's the randomized part of this algorithm?
PIT.
Oh, I see.
There's inside it, there's some kind of, so I'll talk a little bit about it because we're going to de-randomize it. So the I'll tell you where the where the randomness comes, how so you'll see where it is. But he needs randomness in order to output factors, and in some sense randomness is necessary, because if you can't, given an arithmetic circuit, if you can't even decide if it's 0 or not 0, how are you going to factor it? I mean, PIT seems to be a prerequisite in order to factor it.
So you need PIT to do the algorithm, but the
output is a deterministic. Output you use some randomness, and then you output with high probability your output will be good, and the output is a deterministic arithmetic circuit. Yes. And Kaltofen and Traeger showed how to do black box factorization, which means you don't even see the arithmetic circuit, but you're given a black box. We have black box access to a small arithmetic circuit, and then you do some randomness, you do some stuff, and you output black boxes for its factors. So you have black boxes where you can, so for every factor you can evaluate it at whatever point you choose. Okay. And this white box algorithm in particular implied that polynomials with small arithmetic circuits has factors which are small arithmetic circuits. Again, this is itself is highly non-trivial and a very elegant statement, and very surprising that such a statement should even be true. And they both randomized. Good. And can we de-randomize? That's a very nice question, but as I said, I mean, this is at least as hard as PIT. So to de-randomize factoring in general, you would have to de-randomize PIT, and this, as we all know, is hard.
Small arithmetic circuits are small arithmetic factors that are small.
Yes.
Does this fact require PIT, or does it just follow from the fact that you have such an algorithm given whatever time?
It follows from the algorithm. Yeah, that doesn't need PIT. I mean, the fact that, I mean, no matter what you do in the end, you're outputting this. I mean, you can run that algorithm could run.
Doesn't bother you?
No. So at least if you looked, so
You
maybe.
say something about the algorithm, right? I mean,
Right, yeah.
you'll see.
No. So I'm not going to. So in what I, so I'm going to talk about the black box algorithm. I won't talk about the white box algorithm. And the black box algorithm doesn't have this consequence that factors of small circuits are small. So you won't, in what I talk, you won't see any of that.
But you do see it, because you're creating circuits that uses the black boxes. So you do see it. Right? I mean, what
In what I say, you will end up not seeing it. But yeah, we can talk. Let's talk later. There was recently. Okay, so let me. So the polynomial identity testing, I guess everybody here knows. You're given a polynomial computed by a small arithmetic circuit. Decide if the polynomial is identically 0 or not. And this is again very, very natural, has lots of applications, and we know a very simple randomized algorithm, just evaluate it at a random point. And this is probably one of the most natural problems for which we know such an easy randomized algorithm, but nothing non-trivial that is de-randomized. And de-randomizing it again has very nice applications. This would imply superpolynomial circuit lower bounds. We believe de-randomizing is a hardish problem. And recently, in joint work with Swastik and Amir, we showed that de-randomizing factorization is equivalent to de-randomizing PIT for polynomials in VP. So if you can de-randomize PIT, you would de-randomize factoring, and the other way around. And this is in both models, white box and black box. So even the PIT question you can ask in the black box setting and the white box setting. In both settings, factoring and PIT are equivalent. And so,
in other words, if you have an oracle for testing 0, then you
Right.
can factor deterministic.
That is right. So if you have an oracle, if you can decide, if you have someone who will tell you, given a small arithmetic circuit, if it's 0 or not, you can use it to deterministically factor. That is right.
And counterexamples is also true for white box derandomization, or does it require
White box. I think black box derandomization implies circuit low bounds very easily,
I see.
because you have a hitting set, a small hitting set, and once you have a small hitting set, you can interpolate, and that the polynomial that you interpolate cannot be computed by a small arithmetic circuit. So black box derandomization of PIT very easily implies low bounds, and the white box is the hard one.
It's an old result of Heinz and Schnorr, and in the black box model, which is much easier, it also gives arithmetic circuit low bounds directly because of this interpolation. The covariance impedance is more involved, and the low bound it gives is either an arithmetic low bound or a Boolean low bound.
Right. Good. So this derandomizing factoring is equivalent to derandomizing PITs. This holds for polynomials in VP, so small arithmetic circuits. You could ask, look, I don't know how to derandomize PIT in general, so I don't know how to derandomize factoring in general, but I do know how to derandomize PIT for special classes of polynomials. I do know how to derandomize PIT for sparse polynomials. Can I use it to derandomize factoring for sparse polynomials? Or in general, any class of polynomials for which you know how to derandomize PIT, maybe one can try to think about derandomizing factoring for that class of polynomials. And probably the easiest and most natural class to look at is sparse polynomials. We know for a long time we've known efficient deterministic PIT for sparse polynomials. So can we do derandomized factoring for sparse polynomials? So that's a very natural question that comes up. So Clivens and Spielmann give this factoring, the PIT algorithm for sparse polynomials. Can we use this Clivens-Spielmann?
It's much older, like Benoit, but this is about interpolating. I mean, just
Yeah,
learning.
maybe, right.
This is like from the 80s.
What do Clivens-Spielmann do? Which is
but
reconstruction?
they do more
Reconstruction?
fields,
I'm not sure what they do, which is reconstruction.
Benoit also does reconstruction.
I don't know. So anybody know?
Benoit and Tiwari, right?
Benoit Tiwari.
Yeah.
So what do Clivens-Spielmann do?
Remember, but
Hitting set? No, hitting set. Of course, it's a hitting set.
It's low randomness polynomial identity testing. So
Yeah,
you
maybe
trade
the-
off the amount of random bits you use with the amount of work you do.
Yeah. So this shouldn't be the citation. We shouldn't keep talking about Clivens-Spielmann in our paper because but we don't care about low randomness. Okay, so yeah,
it's
so
simple also, but there were all the results, and certainly in
Right.
the 80s
Right. So they also do it, and maybe they do it well, and they have reconstruction algorithms and good parameters that are so good. This is known since much before their work. But for sparse polynomials, so good. We know how to de-randomize PIT. We know lots of things for sparse polynomials. We know how to reconstruct it. So we know that even if you can't see the sparse polynomial, you just have we have deterministic algorithms for reconstructing it. So we can construct a deterministic set of points, so that if you know the value of the sparse polynomial at those set of points, not only can you decide if it's 0 or not, you can even recover what that sparse polynomial is.
It's a natural generalization of the univariate case. If you evaluate a univariate polynomial in degree d plus 1 points, then you know the coefficient.
Yeah.
But,
So it's a natural generalization, but this is much harder, clearly.
What you know, the number of degrees of freedom is the number of coefficients.
Yeah.
And,
Right, but there clearly they don't need randomness. Just d plus 1 is enough. Here,
not randomness. There's a deterministic one for.
there's something for sparse, but this is much more non-trivial, right? When you look at it, it's not clear.
It's not clear, but it's not so complicated.
It's not so complicated, but if you have right.
That's why I said it's a natural
Right,
generalization.
right,
It requires
right.
an idea, but it's
Right,
doesn't require hard work.
right. Good. So it's a nice question to ask about de-randomizing factoring for sparse polynomials, and for the same. So we can't do it for general sparse polynomials, which is again a beautiful question. But we do it for this in sparse polynomials with this bound on individual degree. We then do de-randomized factoring. We get this quasi polynomial bound, s to the sum power of d times log n. And if you get rid of the log n there, it would improve. The log n wasn't necessary in the sparsity bound. So if you shave off the log n in the sparsity bound, it would shave off the log n from the factoring algorithm as well. Okay. And for d equal to 1 and 2, we knew deterministic algorithms, and for general d, this is what we show. So let me tell you what ideas go into the proof. So before I tell you so I'm going to tell you the ideas in our for our de-randomization. But before I tell you what ideas went about the de-randomization, let me tell you about something about the randomized algorithm from the past. And this will be the one which is most relevant for our work is the Kaltofen-Traeger randomized black box factoring algorithm. That is the one which was most easily adaptable to our setting. So for general polynomials, so this is how the Kaltofen-Traeger algorithm worked. So your input is black box access to an n-variate polynomial computed by a small circuit. Your output, you want black box access to its factors.
You don't need that it's computed by a small circuit, you just have a black box.
It needs a smaller, I think the proof doesn't need small circuit. I'm not sure, does it need small circuit?
You need the Hilbert irreducibility.
Hilbert irreducibility. And a small degree is
The degree, yeah, of course you need the degree.
PI, but if you need PIT, don't you need to do PIT for a small arithmetic? If you're going to use
Sorry, right, and you use the PIT.
No, but PIT you can do for black box.
Yeah, for black
Using
box you can,
using
yeah.
randomness.
Yeah.
You can do black box.
Yeah.
even if it's a large circuit.
Yeah, just the
It's a degree bound.
Yeah.
Yeah, good.
There is no.
Good.
But that you need in white box also, the degree bound. The degree bound is always.
Yeah, so good. In a world where you have any hope of de-randomizing it, these better be small, because if they're going to be big, there's just no chance of de-randomizing it ever. But if you don't care about de-randomizing it, then Schwarzschild, just identity testing you can do as long as you know a bound in the degree. You don't need a bound in the size if you're free to use randomness. So good.
So for the Kaltofen-Traeger, you don't.
Good. So for Kaltofen-Traeger, you didn't need the black boxes to be small arithmetic circuits. But when we will try to de-randomize it, it will be nice to think about it as small circuits, because we'll want to de-randomize and then it will matter. But just by default, you have polynomials sitting inside black boxes with a upper bound on the degree. So we can hope to at least check if the polynomial is zero, non-zero, and things like that. And you want to output black box access to its factors. Again, since it's only black box access to its factors, it doesn't matter if the original circuit was huge and the factors are huge. It doesn't matter, because the output is only black box access. We never really need to compute that factor completely. And so here, let me tell you so the 4 steps which go into the algorithm, high level steps, and I'll elaborate a little bit. There's one pre-processing step to make f monic. It's a technical, bit of a tedious step. Let's not talk about it. But you can assume your polynomial is monic, do some transformation of the variables and make it monic in a particular variable. So for instance, if your variables are x1, x2 up to xn, you can imagine it's monic in x1. So there's one pre-processing step.
Just divide by the coefficient.
The coefficient might be it's not a coefficient in the field. The coefficient of x1 might be x2. This is a multivariate polynomial, so it's. But I believe you take a random linear combination of all the variables, a random linear transformation, it will probably make it monic. So just a random linear transformation, then one of the variables will probably come out. So and why is it so that would work? Maybe it needs a proof.
By keeping individually these.
No. I'm talking about Kaltofen-Traeger. Yes, but the other ways around it. So you can, without doing this random linear transformation, there's other, by now standard ways. Let's not talk about that now. But this is now it's not hard, but it's a little tedious. Good. So the first step is make f monic. Second step is you take this polynomial which depends on n variables, and let's make it depend only on 2 variables. You project it down to a random 2-dimensional space. Okay. Once f is a polynomial which has been projected to a 2-dimensional space, the polynomial f depends on only 2 variables. And if it depends on only 2 variables, then we know then factoring is easy, because this is something separate. We know if the polynomial is only constantly many variables, we know how to factor. So factoring is easy once it's 2 variables. And the crucial step in Kaltoff-Traeger, the crucial ingredient in the proof is the lemma, the Hilbert irreducibility theorem, which says that if this projection was a random projection, then if you start with an irreducible polynomial and you project it to a random 2-dimensional space, the irreducible polynomial will remain irreducible. That's why you don't project it to a 1-dimensional space. A multivariate polynomial, if you project it to a 1-dimensional space, a univariate polynomial always can factor. But if you project it to a 2-dimensional space, this Hilbert irreducibility theorem shows that an irreducible polynomial will remain irreducible upon this projection. And so now if your polynomial f was a product of some factors, you project it down to a random 2-dimensional space, then it won't subfactor. The factorization, the pattern will stay the same. Each irreducible factor will remain irreducible. So the whole the template or the factoring pattern of the projection will be the same as the factoring pattern of the original polynomial. Yes?
This may be stupid, but is this like for any field or a big enough field, this irreducibility theorem?
Big enough field because, yeah, big enough field. Good. So this needs a PIT. So the proof of this Hilbert irreducibility needs a PIT inside it. So basically, as big of it's going to be, the field has to be probably polynomially larger than the degree of the polynomial to make this work. And underlying this Hilbert irreducibility theorem is, so the randomness is in the choice of this 2-dimensional subspace, and there's a PIT underlying everything. If the coefficients of this 2-dimensional subspace have to be a hitting set for a certain polynomial, and if they do hit a certain polynomial, then this would be irreducible. So
not only is the pattern the same, it's every factor in the 2-dimensional subspace is a projection of the original factor.
That has to be anyway, right? Because
it has to be. I'm just
So exactly. So every factor, the 2-dimensional, every factor of the original polynomial, had you projected that to the 2-dimensional space, that would have been a factor of this 2-dimensional polynomial. So the factoring pattern stays the same, and the factors are in 1-1 correspondence. The factors of these 2-dimensional factors versus the n-dimensional factors, they are 1-1 correspondence. Every factor of the n-variate polynomial, had you projected it, you would get a unique factor of the projected polynomial.
So this happens with high probability?
This happens with high probability depending on this random 2-dimensional space. We took the randomness, it's a choice of the randomness. So let me state this Hilbert irreducibility formally. Maybe it's instructive to see that. So this is the theorem. So so I'm just doing it in a language which will be convenient for what is coming later, what I'm going to say. So let's treat it as a polynomial in n+1 variables. So y, x1, x2, xn. So I have a polynomial. There's one variable is a special y variable, and the remaining is x1 to xn. And my polynomial is monic in y. So the kind of Hilbert irreducibility I will, the form I'll state it in, it'll be useful to have it monic in y. Though I believe this is not important. If my random 2-dimensional space was chosen uniformly random from all 2-dimensional spaces, I think this monic is not going to be necessary. But the form I will state it in, let's assume it's monic in y. Total degree is d, and there's this other condition, at least the way the Hilbert irreducibility is stated, which I don't, the derivative in y is non-zero. So for characteristic 0, this is unimportant. if it's monic in y, the y derivative will not be 0, but over fp maybe funny things can happen. So for now, let's assume that we have this condition. It's not hard to enforce this condition anyway, and it simplifies the proof. So good. So let's say f has all these conditions, and suppose you also know that f is irreducible. Irreducible. Then let's look at the probability. Let's sample vectors a and b uniformly at random from, so just like you do PIT, there's some big set S, and let's look at S to the n. Let's sample a and b uniformly from this big grid. Then the probability that f, let's leave this, so I'm not projecting to a uniformly random two-dimensional space. I'm projecting to a two-dimensional space which looks like the following. The y variable is untouched, and I'm looking at a1t plus b1, a2t plus b2, a(n)t plus bn. Let's look at this polynomial. Okay, so I've projected down to a two-dimensional space, but it's not uniformly random over all two-dimensional spaces because I've left y untouched. Then the probability that this new polynomial is reducible is at most O of d to the 5 divided by size of S. So as long as my a and b are sampled from a large enough grid, then with high probability this new projected polynomial will be also irreducible. So this is the kind of projection. This is the second step. You project to a two-dimensional space of this kind. Now it's a polynomial in two variables. Let me call this polynomial f sub a comma b of y comma t. This is a new polynomial, only two variables, y and t. The coefficients depend on the random choice you made of a and b. So this polynomial, this two-variate polynomial, if f was irreducible, this two-variate polynomial is going to be with high probability irreducible. And in particular, if f factored as a product of certain number of factors, and you do this projection on f, all the irreducible with high probability, every irreducible factor will stay irreducible. And to make this high probability, this is a union bound over all factors, so I'll take S suitably large and say that all the factors must stay irreducible.
How do you test whether one factor becomes reducible or not?
I won't be able to test. So,
No,
sorry.
In your analysis to get this union bound.
So there's some PI, I mean there's a PIT. This will, if a irreducible factor becomes reducible, it meant that some big determinant was 0. And if as long as these A's and B's are hitting sets for that, this would stay irreducible.
And just out of curiosity, this sound improves if you take projections into three-dimensional spaces or four.
This bound of d to the 5 over s, I'm not sure if it improves. I don't know how optimized this is d to the 5, so I don't know how much. I'm not sure. It sounds like it should be easier for it to stay irreducible the higher the dimension is, but I don't know if there's a quantitative improvement in that one. I don't know.
This is true with d square. I mean, most recently by lesser.
I see. Okay. Even in two dimensions, and
Yeah,
must be
random two dimensions, d square upside
okay.
by lesser.
Okay. Good. So this is key. So once we have this lemma, the rest of the factoring algorithm is actually not very hard. So this is also no. So the Kaltoff-Traeger randomized black box.
I mean the rest of the steps.
Rest, you said, oh, rest of this has a deterministic also. The randomness is only in this. There was possibly randomness in this pre-processing. I don't know, but maybe you can do that without randomness also. The main use of randomness was this Hilbert irreducibility. Once you have this, yeah, the rest of it is deterministic, and let me tell you what it is. So you project f to this two-dimensional space and you factor it. Okay, the factorization pattern now you got. Now you want to evaluate the factors of the original f. The goal is to output black boxes to the factors of the original f. So you want to output the factors of the original f, the values, the evaluation of the factors at any chosen point. So suppose someone tells you this is okay. Suppose someone tells you evaluate the ith factor at the point alpha. What would you do? So the picture is the following. So I have projected f to a two-dimensional space. I want to evaluate any factor at a particular point alpha. So I look at the three-dimensional space, which is a span of this two-dimensional space and this point at which I want to evaluate f. So I get a three-dimensional space. So look at, so this two-dimensional space was V. V sits, this is the two-dimensional space. V sits inside V prime, which is the span of V and some point alpha that you want to evaluate f and any factor of f at. So look at this three-dimensional space and now look at the projection of f to V prime. Instead of projecting f all the way down to V, project f to this larger space V prime. It's a three-dimensional space now. And factor f there. Now, if for V we had this strong guarantee that irreducible factors stay irreducible, then for V prime also we have the same guarantee because V prime is bigger than V. So if an irreducible factor stayed irreducible on V, it can't reduce on V prime. So if V was a good two-dimensional space, V prime will also be good. And we factor f on V prime, and now we can also we have a 1:1 correspondence between the factors of V prime and the factors when projected to V, because the factorization pattern of V was the same as the original pattern. So the factorization pattern for V prime is also the same as the original pattern, and there's a 1:1 correspondence for every factor on V prime. You can match it to whichever the corresponding factor on V by seeing how the factors project. So there's an easy way to get a 1:1 correspondence between the factorization on V prime with the factorization on V. And once we have a factorization on V prime, we can evaluate any factor at that point alpha you wanted, because alpha sits inside V prime. And that's it. So now every factor, that's how you evaluate it at alpha, because you have the factorization on V prime. You know the 1:1 correspondence, how these factors match up with the factorization on V, and now you evaluate it at the point alpha, and you got the value of the original factor alpha. Any questions, stop and ask me. This is simple, but it's clever.
So this two-dimensional factor will give you each of the factors as black boxes, or not?
The two-dimensional factor we can actually reconstruct. We have it in our hand, the two-dimensional factors.
Oh, you have it in there.
Because it's two dimensions, so it's sparse. If the overall degree was small and your polynomial depends on only two variables, then the total, you can actually by interpolation, maybe good to know, you can actually recover it.
This correspondence between factors is easy to get at.
It's easy to get. You can actually look at the factors. When the number of variables is small, you can by interpolation you can reconstruct these factors, and so you can see. And so you can just get the correspondence is easy, and now you just evaluate these lifted factors at the chosen point. And now for every point B, you look at now from some other point you get another three-dimensional space. So for each point you want to evaluate it at, you'll get this new three-dimensional space, but all these spaces will contain V, and so that ground factorization pattern is fixed. And now each time you have a new point, you lift it to the three-dimensional space, find the correspondence, and then evaluate it at the point.
So what this really gives it was discussed for a particular point alpha, but you can see that alpha can be an input to a circle that with orcal access to the original polynomial will produce a value on every factor.
Right.
And that's how you reconstruct the result about the small circles.
Okay. So that was Kaltoff and Traeger. So now in order to So now we have, in our setting, we have sparse polynomials. Good, and we want to hope to de-randomize this algorithm. So this part is fine. There was no randomness. The randomness, this pre-processing is also we can do without. This can be done deterministically. It's a little bit messy, details, the individual degree, sparsity, all that. Little bit messy, not interesting, tedious, and no randomness. Can be done, pretty standard. So just trust me, this step doesn't cause much of an issue. Is this projection, this Hilbert irreducibility, the heart of the randomness is coming from this Hilbert irreducibility theorem. And so we want to be able to de-randomize this. And we don't know how to de-randomize it. It seems hard. Even for sparse polynomials, this the Hilbert irreducibility theorem, the kind of PIT which arises even for sparse polynomials is a complicated PIT. And we don't know how to de-randomize the Hilbert irreducibility theorem. So we need to get around it some other way. So we are not able to project to a two-dimensional space and hope that it stays irreducible. That we are not able to do that. So good. So there's these 4 steps, right? Pre-processing, projection, factoring the projected f, and lifting the projected factors to evaluate it at any other point. This pre-processing step for now, it's a little tedious because to ensure that in this while you're doing this pre-processing, you don't ruin sparsity and this individual degree bound, but it can be done. Monic, here you didn't really see why monic mattered, right? At least in the way I presented it, maybe you could have done it without monic, who knows. But for us, this pre-processing to make monic is going to be actually super important. And one reason is the following. Our polynomial a priori, if it has individual degree d, how many factors can it have? D times n still. The total degree is d times n, it could still have d times n factors. But if your polynomial is monic, it can have only d factors. If you have a monic polynomial and the individual degree is d, the polynomial can have at most d factors. So this pre-processing to make monic, it's hiding a lot of stuff going on inside it. This pre-processing is showing that, saying if you can do monic factoring, then you can do general factoring. Monic factoring, the number of factors is only d. The original polynomial might have had d times n factors, but this is a kind of crucial step where we reduce to the case that okay, it's enough to handle the monic case. Then we will show how to lift it to the general case. And in the monic case, one nice simplification we get is that the number of factors is small. And this is going to be important for us. We won't be able to handle n factors. Think of d to be 5 or 10. So the number of factors is very small. That will be important. Good. So that was one step, which again I'm hiding details. The second step is Hilbert irreducibility step. Project to a random subspace. So we don't know how to de-randomize it in this strong sense, and we won't. But we'll do something else to somehow get around it. So we don't know how to preserve the factoring pattern. So I don't know, we will project it down, but when we project it down, irreducible factors may not stay irreducible. So we'll have to give up on that. So we'll give up on that, but we'll gain something else, something weaker, but it will turn out to be enough. What we will ensure is that if you have 2 irreducible factors of f, when you project it down, these irreducible factors may not stay irreducible anymore. We won't get this Hilbert irreducibility theorem. So irreducible factors might further subdivide, but we can ensure that different irreducible patterns, after their projection, they'll still have GCD1. This will ensure that they won't mix. Irreducible factors, though they might further subdivide, they'll stay separate. Their GCD will be 1. This is a feature we can ensure. So this we will ensure. We'll get a projection that gives us this fact that 2 different irreducible, for an original polynomial, any 2 different factors, their GCD will remain 1 after the projection. And the way we do this is by resultants. If 2 polynomials have GCD 1, their resultant is not 0. So you start with 2 irreducible polynomials, distinct. We take the resultant with respect to a certain variable. The resultant will be a non-zero polynomial we'll find a hitting set for this resultant. This hitting set, this resultant will look nice. If our original polynomial is sparse and small individual degree, these resultants will look nice. And so by Benor, Tiwari, we can find a small hitting set for the resultant of every pair of polynomials.
So what's the general statement here that you can you have a PIT in particular, you have a PIT for result. You have a deterministic test for GCD1 of multivariate polynomials.
These are sparse polynomials of low individual degree. We will use that.
For your polynomial,
So if
you have a deterministic test of GCD1.
yes, yes. If two sparse polynomials of small individual degree, we have a deterministic test to test if they have GCD1. Exactly. And maybe I'm running out of time, otherwise I could have said more about this. Maybe I can say more. So anyway, so for those of you who don't so let me see what I want to say about this. Maybe I'll say this here. Actually, let me write it out. So you have a polynomial f. Sorry. If two polynomials, they're sparse and small individual degree, then the GCD of f and g is 1 if and only if the resultant with respect to the variable y of these two polynomials is not identically 0.
I'm not sure everybody knows the definition.
So you know, so this resultant is going to be a polynomial. So these were multivariate polynomials. This statement I could have made if these xi's were even field, just for univariate polynomials, if these xi's were just field constants. This is a statement which is still true. The resultant, if now for multivariate polynomials, the resultant with respect to y of these two polynomials is going to be a polynomial in the x1 through xn's. So this is so this resultant is a polynomial in the variables x, and it turns out to be a 2ds to the 2d sparse polynomial. So this resultant is a polynomial which ends up being sparse if our original polynomial was sparse, and the resultant, I can just give you the definition of what the resultant is. So if f individual degree, so we have an individual degree bound on f and g.
Yeah. So in the resultant you just get the sum.
You get the sum. It will be also low individual degree. We don't care about that really, but it will also be low individual degree. Yes. So if f is a polynomial ad y to the d plus ad minus 1 y to the d minus 1, and g is a polynomial say b sub e y to the e plus d0. It's some polynomial in the y variables. The coefficients are these ads. They could be field constants, they could be polynomials themselves. Then the resultant is this big matrix. It's a determinant of a big matrix. It's a d plus e by d plus e matrix, and each entry of the matrix is one of these coefficients of these polynomials. It's going to be ad minus 1. Right. The first row will be all these coefficients followed by some zeros. The second, sorry, that's the first column. The second column is some shift of the first column, and so on and so forth. So each entry is either 0 or one of these coefficients. And you take the determinant, that's called the resultant. The resultant is non-zero, means the GCD is 1. It's a really nice and elegant fact. And if all these ADs were sparse polynomials and D and E are small, then this determinant is also going to be a sparse polynomial, because it's a small dimensional determinant with entries being sparse polynomials. So all these, so the low individual degree got really used, right? Because the lowness of the individual degree, maybe this is really where we use, or this is one crucial place where we are using small individual degree, where these resultants are sparse polynomials, because these matrices have small dimension. So we can do this step. We can find a small hitting set, and we can ensure that the GCD of these projections is.
But now you're projecting onto one-dimensional spaces.
I will project onto a one-dimensional space. Yeah. So I don't care. I can give up. Good. I don't care. No, this Hilbert irreducibility I've given up on. So I'm not hoping to preserve irreducibility. I'm only hoping to preserve this GCD fact. And for that, it's okay to go to one dimensions. Didn't have to go to 2 dimensions. 1 dimension was fine. So I will hit that, and it will be a polynomial only in the y variable. Good. Now so I've got a hitting set for the resultant. I don't know if I have which point of the hitting set is a good point. Right? In the Kalthoff and Traeger, here I just pick random A's and B's, and with high probability they're good. I didn't have to try out all the points from a grid. Now if I have a hitting set, that means one of the points of my hitting set is a good point. This GCD1 thing is preserved, but then the rest of them are bad. How do I know what is good, what is bad? I don't know. So I'll have to try them all out, and I will try them one by one. For each try of the hitting set, I will produce a factoring, and I can eventually, once I produce a factoring, I can test if a factoring is good or not in some brute force manner, because if I output the factors of a polynomial, and I'm living in this world of sparse polynomials, I can interpolate, recover the factors, brute force multiply it out, and check if my factoring was a good factoring or not. So each time I make a bad choice, I know that my choice was bad in the end by testing and pruning out. So I can always run over everything and then prune out all the bad stuff along the way. So I can know, let's pretend that we got a good hit, and this factor is correct. So I take a univariate projection with this property that the GCD stays 1 of irreducible, 2 distinct irreducible factors.
So before you get to this, so the key point here was just that the resultant is a sparse polynomial, and therefore you can deterministically
Good. Yes.
do a hitting set.
Yes. So result was sparse, and so there was no randomness needed. Deterministically, one could find a hitting set for the resultant, and so deterministically one could find a good projection, whereby good projection it's one where if 2 factors have GCD1, after projection they still have GCD1. And that was the only fact I ensured. Good.
So it is interesting if, some closure properties for PIT. Like if you have a deterministic PIT for some class of polynomials, we have it for the resultants.
Right.
So you have at least one class.
Yeah. Good. So for Hilbert irreducibility, irreducible factors stayed irreducible, and so the factorization pattern of the bivariate polynomial was the same as the factorization pattern of the global polynomial. In our case, when you project down to 1 dimension, an irreducible polynomial might further subdivide, and so we haven't preserved the factoring pattern. So once I go down to this 1 variate polynomial and I factor the 1 variate polynomial, how do I know how to club my factors together to correspond to the global factors? Right? Maybe my global polynomial has 2 factors, but my univariate polynomial has 10 factors. Then I need to know how to group these 10 factors into 2 groups corresponding to factor 1 and factor 2. In this setting, it was easy because the number of factors was the same. In our case, it's not as straightforward. So we need to find the correct grouping corresponding to the true factorization. But since I only d factors and d is small, the total number of groupings is just exponential in d. Try them all. This is brute force. Another place we're using this small individual degree. Try every possible grouping and pretend you got the right one. because all the bad ones you prune out in the end by testing it out. We have got
Anyway, the bound is exponential in D.
anyway, it's exponential in D. This loss of D is we can easily handle. So try out all possible groupings. You know one of them is the correct one, and let's pretend we know what that correct one is. Because if you got a bad one, eventually when you will factor it, you can test and see if your factor was a good factoring or not. So let's pretend we got the good grouping. So that because the individual degree is small and hence the number of factors is small, this we got this univariate polynomial. We pretend we know the good grouping, and this GCD fact we have. And so now the only part left was to lift these projected factors to be able to evaluate them at any point. We'll use the same Coulter-Fintrager idea. So again, if we want to evaluate our factors at some point alpha, we will look at the span of V and that point alpha. Now this will be a bivariate thing, because univariate plus one more point, you got a bivariate polynomial which we project f to that and factor it there. In the original Coulter-Fintrager, like I said, the factorization pattern is unchanged, so there's then this easy correspondence between the factors of V prime and the factors of V. In our setting, there's no such easy correspondence, because the pattern on V might be a subdivision of the pattern on V prime. However, this fact that irreducible factors have GCD1 saves us, because if we know, so these two facts, the fact that this is GCD1 fact that we ensured, plus the fact that we know the good grouping for the univariate polynomial, these two facts, once we have it, it's I have 5 minutes, so this is the last part of the proof. Let's see why these two things tell you how to get a correspondence between the factors of V prime and the factors of V. These two properties will allow us to compute the correct grouping for V prime and get this correspondence, and once we get the correspondence, we can just evaluate those factors on V prime at whatever point we want. So the main key step is to do this. I don't think I have any more slides, right? Good. So let me tell you, this is the last part, how to get this correspondence, and then that finishes the proof. So good. Let me convince you. Let me convince you by an easy, simple example. So say f equals g times h. That was the original factoring. There were just two factors for now, just assume. And let's see why. And now you project it, right? You have f projected down to v, and this has many factors. Let's call this h1 times h2. Okay, now f projected down to v has many more factors, right? It is g1, g2, g3, gk. Okay, because it might further subdivide. But I tell you, I also know the good grouping. So suppose I know that g1, g2 was one good group, and g3 to gk was the other good group. So I pretend I know the good grouping. So I know that h1 on projection is g1, g2, and h2 on projection is g3 up to gk. So I also know this. And since h1 and h2 are distinct factors and they're irreducible factors, their GCD is 1, so the GCD of these two things is 1. Okay, so let's pretend I have two buckets. Okay, I put g1 and g2, that this is the grouping, into bucket 1. I put g3 up to gk into bucket 2. And these buckets correspond to my two original factors of f, and these two buckets have GCD1. Now when I look at f projected down to v prime, okay, and I gh, and I have factors, what's a good letter, m1, m2, mr. I need to know how these factors, how these mi's correspond to these mi's also. I need to find the good grouping of these mi's. Which one corresponds to h1, which one corresponds to h2. So each of these mi's has to go into one of these two buckets. So the step in my algorithm is to find that good grouping here. And now I look at m1. Which bucket will it go into? I need to see. So m1 is on v prime, right? To see which bucket it will go into, I project M1 down to V, and I have to see, and then once I project it down to V, it's going to be a product of some of these GIs. So which bucket will it go into? It will go into the bucket which has those GIs. Can there be some confusion? Maybe it could have gone into this bucket and that bucket? No, it can't have gone into this bucket and that bucket because the GCD is 1. Since the GCD of these two buckets is 1, these GIs are completely distinct. So there's no confusion. This GCD1 property ensures there's no confusion. When I look at M1, I know which bucket it has to go into. I look at M2, I know which bucket it has to go into because when I project it down to V, there's no confusion. And this GCD1 ensured the no confusion. So hence for every, so I can, given that I know a good grouping on V, I can lift it to a good grouping on V prime because of this no confusion fact because of the GCD1. And then I can evaluate the factors at whichever point I choose, and we're done. So that finishes the proof. This was just the summary of what I said. You pre-process, project, factor, lift. And there was this testing step, right? All these bad choices I might have made, bad groupings or bad elements of the hitting set. How do you test if a factoring is good? If I have access to sparse f g1 to gi, and I'm going to check if f is the product of gi, using again Ben or Tiwari, I can reconstruct the sparse polynomial and reconstruct these f's and gi's and test if f is indeed a product of gi. So that's it. So these were the two results again that we showed. Open questions. Improve the sparsity bound, I think is great. So that there's lots to be understood and various settings. Quasi polynomial to polynomial, that's the log n need not be there. Plus, I mean, if you can use field information and stuff like that, we can probably hope to do much better. Yeah, and even without having a sparse, one could have hoped to do deterministic factoring of sparse polynomials even without a sparsity bound. Because if you want to do this in the black box model or whatever, you don't even, we use the sparsity bound to do the factoring. But maybe even if the sparsity bound is not true, maybe one can still do factoring. So you could ask this question. Or another question is, what if you, I don't know, what if you know the sparsity bound? What if I tell you that factors of sparse polynomials is sparse without this individual degree constraint? Can you use it to construct a deterministic factoring algorithm? We don't know how to do that. We use a small individual degree crucially in the sparsity bound. We use it crucially in the factoring algorithm. And yeah, again, deterministic factoring for other classes which we know PIT for, that's another good question. And I'll end here. Thank you.